Hello, everybody, and welcome to another edition of Telescope Talk Pro, our weekly look into the exciting discoveries and projects being done by professional astronomers from all over the world using ground-based telescopes. My name is Tony Darnell from deepastronomy.space, and today we are going to learn about a new project being built right now, something I'm very excited to talk about. It's called the Large Synoptic Survey Telescope, which is currently being built high in the Andes Mountains of Chile on the Cerro Pachon Ridge in north-central Chile. It is an 8.4 meter telescope, and it's using a special 3-mirror design, creating exceptionally wide field of view, and has the ability to survey the entire sky. Get this, folks. I cannot say this enough, how amazing this is enough. It can survey the entire sky every 3 nights. Now, the camera is a little disappointing, though, I have to say. They couldn't do better. It's only got 3 billion pixels. So, I don't know. We'll see. We'll try to get due, I suppose, with a camera like that. But today, we're going to learn about what LSD can do, what science it'll do, and some of the data processing challenges that will ensue when you have a 3 billion pixel camera taking images of the entire sky every 3 nights with our guests from the LSST Consortium. And I'm going to bring them up in just a minute, but I have to say before I get going, Telescope Talk, both the pro and the amateur versions of these hangouts, are sponsored by OPT Telescopes in California. And if you need professional guidance or have any questions about buying and owning a telescope, I can't recommend these guys enough. So check them out. There's a link in the description box below if you have any kind of issues or questions about purchasing a telescope. Now, we are broadcasting this hangout on YouTube, both my channel and hopefully Christian's channel, Launchpad Astronomy.
Yes, we are.
Is it? Oh, good. That's great news. We're doing this from now on just to kind of build some rapport between our two channels, so you can check out our live streams on both of these simultaneously. And we're also streaming on Facebook on OPT's page. We're also streaming on Twitch and Periscope, I hope. So we hope you'll leave us questions and comments on any of these platforms, and I'll read them out to our guests as we go along. So, okay, let me bring up my astronomical Brady Bunch. Where is everybody? There he is. Let me start with my co-host. Right below me is Christian Reddy from Launchpad Astronomy. Hi, Christian.
Hey, Tony, how you doing? And yeah, it looks like the technology is finally working for us today. So thank you for joining me on my channel, Tony, I guess.
Oh, you're welcome. I hope this gets you some subs. If you don't know specifically, I put the link into his channel on the description box on my channel. So please subscribe to him. Sure.
Thank you, Tony. Yeah, you're more than welcome to come over and check me out at Launchpad. But here we are today talking about the Large Synoptic Survey Telescope. And this is something that I'm so excited about because, as Tony said, we're talking about a telescope that will look at the entire sky. If it's in the sky above its location in Chile, LSST is going to see it and watch it and watch it and keep watching it. And that's going to lead to some pretty exciting stuff. So why don't we go ahead and introduce our guest, Tony?
Okay, great. So down right next to me in our panel here is Dr. Yusra AlSayyad. She is a postdoc, and she's also working as the technical manager for the data management team on LSST in Princeton. Hi, Yusra. There you go. You're muted still.
Okay. Right.
Oh,
thanks, Tony, and thanks for having me.
Yeah, you're welcome. And right below her is Frossie Economou. She is also a technical manager for data management, but she is in Tucson. So welcome, Frossie. How you doing?
I'm doing great. It's good to be here.
Oh, I can't thank you enough for being here. So let's talk LSST. Where should we start? I already said it's a 8.4 meter class instrument. Let me put up a quick image here. I'm going to put up the image of the site. This one has it's the one where the building site up on the mountain. This is where they're building it. Why are you building it up in Chile? In fact, why are we building all these telescopes up in Chile, it seems like? Anybody?
Okay, I will
Yusra,
go.
or Frossie, one of the two.
All right, I will go, and Yusra will correct me. So, one of the reasons that we build telescopes in arid and high mountainous areas is in order to ensure the best weather and to be above as much of the Earth's atmosphere as we actually can. So, before a telescope is ever built, there are many years of what we call site surveys, where people camp out there with instrumentation and sky monitors, and they try to characterize how good a site is going to be. We're spending a lot of money on these telescopes and a lot of effort, and every cloudy night that you are close to not being able to do astronomy is time and money down the drain. And so we're looking for the best possible weather.
And it turns out, actually, that Chile is a pretty science-friendly country, isn't it? This is kind of a source of economic benefit for these guys. I mean, it's not just you guys. There's also CTIO is out there, the Cerro Tololo International Observatory, or Inter something observatory.
Cerro Tololo Inter-American Observatory.
Inter-American. I knew it was something weird like that. But they're up there. That's where the Blanco 4 meter is. I went to that mountain. And then, of course, Gemini South is there. So there's lots of major observatories are being using these mountains as a site. Okay, I want to put up just real quick so people can see this is the one you guys just uploaded. By the way, let me just mention, everybody, that all of these images and graphs that we're going to be showing you are available on the Google Drive folder. The link to that is in the description box of the YouTube video. If you go there, you can download all of the stuff and look at it yourself. All the stuff that we're going to be showing you here. They've given us permission to show that. So let me now put up the image here. This one's called Image 9036-1, guys, the one that you uploaded. I have to tell everybody this because they need to have it up locally because they can't see what's being broadcast. This is a scale image of the telescope itself, right? By scale, I mean there's people at the bottom, so you can kind of see how big this thing is compared to a person.
Right, and as you can see from the telescope side, the main part of the building is, doing really well. It's almost complete, so we're very excited to finally see a real telescope on the mountain as opposed to the artist's impression of what it's going to look like. You will see the dome is still going up, and people will be very happy to see the dome completed. I think they've had 2 winters without a dome where it snows in the building, and so we're all going to be happy when the dome goes in, and then the work of installing the scientific instrumentation can proceed. Okay,
and so the dome is that scaffolding part, right? It's not really a dome.
Correct.
It's just
that's right. It's the structure for the. It's for an astronomer. It's a dome, even though it's not necessarily dome shaped.
Yeah, I know. We can't get rid of it, can we? Because it turns out that observatory design has changed over the decades quite a bit. Actually, it's not so advantageous. I mean, what do you need the curved shape for when you've got these alt-azimuth or these actually azimuth rotation abilities of these structures? And you can just open a whole doors to the telescope to see the sky. Okay,
and telescopes are getting larger. I'm sorry, and telescopes are getting larger and larger, so it is driving us to new buildings.
Yeah, the domes would have to get larger and larger as well. So the idea is that this is more. You can sort of see it in the scaffolding, but this is kind of more like a cylindrical enclosure, less of a dome, but more of a cylinder. So the idea is that, can you tell us how that works? When the telescope moves, I take it that the cylinder just moves right along with it, right?
The dome tracks the telescope, and this is what I'll point out that we're software people, so don't ask too many questions as to the nuts and bolts. But yes, there is tracking, and so the opening of the dome, like in every other telescope, will move with the telescope. With LSST, this is particularly challenging because the telescope is very fast, as you mentioned, is wide and fast and deep, and you need to anticipate where the telescope is going to go next, and so that you can start moving the dome to the next position before you necessarily finish where you currently are without occluding your current observation. And Yusra could tell you a little bit about the scheduler that is being used to plan the observing, as she worked with that team as well.
Okay, well, I'll do that, and I want to, but I want to let me just show a couple pictures of the telescope, and then we're going to move on to the software that you guys are working on. So this is the mirror. This is the primary. Now, I wish I had the ray tracing of this, because it is a very strange mirror design, and we're going to have another hangout on that, but we're not going to go into depth with it here today. But it's basically the primary has two different figures on it. It has a one shape that kind of goes in toward the center that I don't know what it is off the top of my head, but then it has another figure deeper in the center, which gives it this sort of strange optical ability. And we're going to talk, like I said, we'll talk about that in another hangout, but I wanted to show you the picture. This is the primary mirror standing up with some people, and one more. There's another view here. I'm showing telescope.jpg. And also, just for grins, let me also image. This is a truck pulling what what is this, Yusra? You tell us what you gave it to us, I think. So to describe what this is.
So our various pieces of the telescope are being taken down from where they're being assembled and moved to Chile piece by piece. So this is the coating chamber. It's the bottom half of the coating chamber that has just been shipped. And it had been split in half, and this is a truck taking it through a tunnel up to the mountain, where you can see it just barely fits. And we were talking earlier about how we have a good relationship with Chile. They're very helpful with engineering and logistical challenges like this when they arise. And
they really are. I mean, I've heard that about, they're very enthusiastic about the fact that their geography lets this be something that they can offer astronomers, and so it's really a great place to be. It's very friendly. And
could I just quickly ask, Yusra, are you saying that this is a picture of the mirror being taken to the mountain in Chile?
Coating chamber.
The coating. Okay, so the mirror is not in there, but it's the coating chamber.
Right, but this is actually a rehearsal because the mirror.
Okay, that's what I thought. Right, the actual mirror has not yet been moved to.
LSST has a coating chamber inside the building to illuminize the LSST mirror.
Okay, so it's going to be illuminized on the mountain.
It's going to be illuminized on the mountain, and when it needs re-illumination, there's this kind of Rube Goldberg pulley system that brings the mirror down and shifts it along, and it goes down an elevator and it falls into the coating chamber, and it gets re-illuminized. And so that is what that piece going in. But of course, it has to be large enough to fit the mirror in. So it's giving you a sense of the scale of what it's going to be like.
So basically, are you moving, like, what is that? You're moving like a concrete dummy, or just do you have an idea? But it's not the mirror.
It is the coating chamber. It is the vessel in which the mirror will go in to get coated.
I got you. Okay, very good. All right.
Wow. That's the chamber that will be spraying the illumination.
Barely fits.
One more picture, very pretty one of the installation at sunset. And everybody, okay, this is why. Look at this picture. This is why you build them in the Andes. Where are the clouds in this picture, everyone? Can you see? They're out in the distance and below the the telescope. All the water vapor is down below the telescope, which is one of the reasons why people pick these sites.
I want to go to there.
It is beautiful. And I'll tell you now, it's the only place I've ever been where the stars, and I'm not overstating this, cast a shadow. I was lost. I know all my constellations, but I couldn't find any of them that night.
Wow.
Okay, and then I think we'll stop with the pictures there for just a minute, except for this one more with the schematic. We won't go into it too much, but you can see it's got the various components to it. It looks like the Hubble from this rendering.
If are you showing the camera, Tony?
Yeah, I'm showing am I showing the camera? I am showing the camera.
So the thing I like about that picture is that it has it's a render because they're still working on the camera, but it has the human for scale. Yeah. And this is actually Nadine, who was the project manager for the camera for a long time, and she's my height. So now, when we show this picture, I can pretend it's a rendering of me, but it's not really. But that actually shows you the scale of the aperture of our 3 gigapixel camera. It's a very large piece of kit.
where it says focal plane and that light, you see those little squares, those are all CCDs, folks. That's where the camera will be imaging from. And that is huge. It's like the size of half the size of a person, just the focal plane. So that is the camera that's going to be used on
and really quick, just for all of our photography fans, why don't you remind us again, Yusra or Frossie, how many pixels are we talking about in that camera?
It is 3.2 gigapixels. So if you
Wow.
were to put that image into 4K TVs, you would need 2 4K TVs for each CCD. And then there's roughly 200 CCDs on the focal plane. And you would require about half of a basketball court to project, to show the 3.2 gigapixels.
The full native resolution, you need a basketball court of 400 4K TVs.
That's right.
Right? Am I counting that right? Yeah. Whoa, that's a lot of data. Is that a problem? I mean, to have that much data. I mean, how much? Well, first of all, you're going to be taking picture after picture after picture of the sky. I mean, maybe you could tell us a little bit about how the telescope will operate, and then I'd like to then talk about what do you do with all that data. So, can you first describe how the telescope will operate on any given night?
Sure. And the data challenge was one of the main reasons why I wanted to join this project. It's part of the fun. So the telescopes, the survey strategy is going to be fully automated. We are going to collect science cases and goals from the community, and these are going to go into a cost function, which we'll be able to optimize. And then in real time, based on this cost function and the weather and the clouds and the conditions where the moon is, it will automatically take picture after picture. Every 30 seconds, it'll take a image that is about 40 times the size of a full moon, and then move on to the next one 30 seconds later, and then move on to the next one 30 seconds later. And in this way, it'll be able to image the whole sky or the full southern sky in just 3 days.
Wow, the entire sky in 3 days.
And okay, so I guess we should probably talk a little bit about the way in which it's scanning. Now, you have this movie. I'm going to put it up real quick. This one is a sort of a GIF. You had it as a GIF image. I've turned it into a movie that shows how the camera will scan an area. It looks like you've got a portion of M31 there, the Andromeda Galaxy, right?
Yes, yeah. And this was a graphic put together by SLAC, the Stanford Accelerator Lab, which is currently the team that's working on the camera.
Okay, so it looks like it's this is showing the different filters, and then it the way it is switching between the different wavelengths, and then is this field of view? Do you know if this field of view is more or less accurate as far as how much of M31 it'll cover?
I believe it is.
Okay.
So now remember the array of CCDs is about 2 feet by 2 feet. So it's this big, and so the filters themselves have to be this big, and
That's right. It's important to remember. See, though, if you look at the left side of this image, you could see the little squares. Those are the CCDs, and we saw how big that was in the other one. That was. Let me put that image up real quick. We saw that was huge. You could see that that's about half the size of a person, and so these filter wheels, as they're coming through, are big. They're really big in diameter, and they're clunking into place. I don't use that word like it's clunky. It's just that it's going to have to. It's a significant amount of weight that you're moving in for all of this. So, what are the typical observing exposure times? Do you know for this when it's in survey mode and looking at the entire sky? What are the exposure lengths that you're going to be taking?
So currently, the baseline is to have 30-second exposure times and have that be the same regardless of what the weather is. on that particular night. At one point in history, we thought it would be necessary to take two 15-second exposures and then add them together. But after some discussions recently, it seems as though that isn't actually necessary to achieve our science goals.
Good.
Okay, so you can just do one continuous 30-second and then just move on. Great.
That's right.
That reduces the overhead time, right? Because you're not spending as much time recycling the camera for another 15-second exposure.
That's right. And when you have 30-second exposures and you're working in survey mode like this, every second counts towards your science impact. Every second you can shave off for readout time, slew time, filter change time, that adds up to more exposures, more science.
Okay, well, that's a good segue into what I want to ask you about now. So you've seen the telescope, we've seen the place where they're building at, we get an idea of just how large it is. What are some of the things? Just give us a broad overview. Just give us a big picture view. What are some of the things LSST is going to be able to give us, and why do we need a survey telescope like this to do it?
So the special thing about LSST is that it is a full time domain survey. It'll create a movie of the sky that lasts for 10 years of the whole sky. And we really we've had very specialized time domain surveys so far, but we haven't really had a complete sky time domain survey. And so this is really going to open up time domain astronomy. So anything that changes, any standard candles that require have special variability signatures to find. These include type 1a supernova or our Lyrae stars. We're going to find orders of magnitudes more of these types of objects. And this is going to impact dark energy, our dark matter, our history of how the Milky Way was formed. Another type of objects that change are asteroids, which are moving across the sky, and you need multiple exposures in order to be able to detect these. We're going to have an unprecedented amount of data of asteroids that we can use to constrain the history of the solar system.
So if you think about just what she just said, a 10-year time lapse of the entire sky, at least as it can be seen from Chile, that will be from 30-second frames, essentially, that imagine the kind of science you can do from something like that. That's quite remarkable. Now we're going to get to the part that you guys are specialists in, which is data management. This is something that's been called big data. We've heard the term. It's a sort of catch-all phrase for everything from medical imaging to astronomical imaging, but it's basically this ability to handle large amounts of data and do things with it. So 3+ billion pixels times, what's the bit depth of the pixel? Couple of are they floats or are they big ints? Do you know how many? Because you have to multiply 3 billion by the depth of each pixel. That tells you how many bytes one frame, how many bits one frame will take. What's the image size of one 30-second exposure? Do you guys know?
It's about 8.2 gigabytes per exposure.
And you're taking 8 gigabytes for one 30-second exposure. And that's the raw data, right? So that's just when you take an image, you come down. You've also, presumably, you still have to take calibration images, right? Let me get to that in a minute. 8 gigabytes of data per frame. And how many frames per night?
Yusra, do you remember? I believe it's about 2,000 if you include all the calibrations.
2,000.
Yeah, about 100 an hour.
Okay, so doing the math in my head.
And it's 18 bits per pixel, since you asked
18 bits per
about
pixel.
The depth, and don't ask me why.
Okay, so doing the math in my head, that's a ridiculous amount of data.
So that's every night.
That is a remarkable amount of data. Over the lifetime of this survey, it's half an exabyte, in fact.
Half an exabyte over the lifetime of the survey. Oh my goodness! Wow.
Wait a minute. What's an exabyte?
Exabyte scale. It's the thing up after petabyte.
It's after petabyte. Okay. You know what? When you hear say exabyte, you know what that reminds me of? Those old DLT drives.
There's little tapes. I know.
Yeah.
I actually, that's why.
No, we're
that's why
talking
I
about
don't
the
like
real
to quote
thing,
it,
real
yeah.
exabyte. Yeah.
I was like, oh, you put it in the exabyte drive, and all it really was these old cheesy videotape tape readers. But
Yeah,
okay.
I know a lot of
that will
our
get you 3
viewers
seconds worth of data. Yeah.
I know a lot of our viewers. You know, they're into tech. In fact, some of them are YouTubers themselves who review technology and cameras and things like that. I wonder if this would be a camera that they might enjoy having for Christmas.
I'm not sure if FedEx ships that size.
Okay, so with respect to okay, so hang on just a second. Let me get to one of okay. So Galaxy is asking, can you please elaborate a bit about its capabilities and instrument specs and goals concerning exoplanets and exolife atmospheres? I can help with this, and I know that you guys are primarily in data management. Well, first of all, do you know the answer to that question? Is that something you can address? As far as how will LSST will it do anything with respect to exoplanets? Like, will a 30-second exposure over a certain period of time allow you to see light curves in variable stars? If you can see these changes in brightness of a variable star, can you see a dip in brightness due to an exoplanet?
Yes. So my specialty is not.
Right, I know. That's
extrasolar
why I know this is a little bit out of your realm. So,
but yes, any time domain survey, you'll be able to see exoplanets eclipsing their host stars. As far as exolife atmospheres goes, there's no spectroscopy on this telescope, but we'll at least be able to find targets for the future.
Right, and that's important because you need, in order to see an exoplanet's atmosphere, it's funny because astronomers make a lot of assumptions. Like if you've got a super Earth, they kind of assume because it's rocky and it's of a certain mass that it has an atmosphere. We learned that in a couple of hangouts ago, where the reason they talk about atmospheres is because the way planets form, if they have a certain mass and if they're above a certain mass, not necessarily even rocky, then they will probably have an atmosphere. That just comes with the way planets are formed. And so if you're seeing a transit go through and you're looking at the light curve, that's one thing, and that's what LSST apparently will be able to have the resolution to see, but it won't have any spectroscopic ability. So that's the kind of thing I go back to to JWST, it's going to need to help us with, because you look at it will have near spec on board, a near infrared spectrometer that will be able to measure the components of what's in any atmosphere that might be present.
And in fact, you're correct. And I shall just say very quickly that if you Google LSST Science Book, you will find a compendium of all the kind of science cases that are behind LSST, and it's really quite impressive how it addresses astronomy on every physical scale. So if you want to know what LSST will do in your favorite area of astronomy, LSST Science Book is where you want to go. If you have insomnia, that might also help you.
You're saying it's not exciting.
Yes. It can get a bit heavy at times. I'm just warning you now.
We're not talking about a pamphlet. We're talking,
we're talking about something heavy enough to be a self-defense weapon. But going back to the issue of spectroscopic follow-up, so LSST is absolutely designed with the assumption that the LSST finds things, and other facilities that have the appropriate instrumentation for following up on it will then follow up with further observations. And this is why our data management system includes an alert system where when the science pipelines detects that something has changed, it will send out a message on the internet that other telescopes can subscribe to and decide whether they want to follow up on something particularly interesting. And Yusra is definitely the person to talk a little bit more about how the alert generation and follow-ups work.
Okay. I will segue you into that, Yusra, by just reading Better and Better's comment on YouTube. He's going, but does it only record changes like a security camera? Well, it records everything, and then you can see changes within the different frames. But yeah, do you want to talk about that a little bit? The transients and the changes in what it will see?
Sure. So it is not like a security camera. We are going to store all the data.
Not just the changes.
Yeah, and because this isn't a space-based telescope, we don't have to worry about data transfer rates, or, I mean, we do have to worry about that, but we're not limited in the same way that space telescopes are limited.
Okay.
So we have two modes of processing. And so the team that I work on is the team that does the science pipelines. And we write the software that converts the pixel data into a database of stars and galaxies. And for each one, it's measurements like shape, brightness, color, size, and all of its characteristics. So we think a lot about how to combine this multi-epoch imaging to extract the most amount of data from it. And we'll be doing this in two different modes. So one mode is difference imaging, and that's to find what has changed in real time. We will build up stacks of all the previous images. This will be a template of the static sky. And for every new exposure that comes off the telescope, we're going to subtract this template from the new exposure, and this will yield a map of what has changed. And I included in the Google Drive an example of what this difference imaging.
I'm showing it now as you
like.
talk, so maybe you can explain the three frames.
Okay, so the first two frames, on the left, on the middle, are two different visits of the same part of the sky. And these images were not taken with LSST because it doesn't exist yet, but they were taken with DCAM, also in Chile. And that's right. Okay, so then the picture on the right-hand side is the first two pictures subtracted from each other. And you can see that the background of stars and galaxies disappear, and all that's left is what has changed, which you wouldn't have necessarily seen if you were just looking for the first two images and then matching all the positions on them. So the object that has changed is most likely an asteroid in this image.
So there's the two frames, the left one, the middle one, the middle, or one is subtracted from the other, and then the far right is the difference, the result of that subtraction. There is a black blob off to the sort of the leftish part of that, and then there are other lighter blobs that are kind of black and white, right? I mean, they have components of a little bit of light and dark. Where's the asteroid?
The asteroid is the dark spot. So in this example, the second image has been subtracted from the first, and the asteroid was in the second image, so it appears as a negative image here. The white and dark blobs, we call those dipoles, and those are the bane of all difference imagers' existences. These are, so if you have a bright star, for any astrometric offset of those two stars, there's a brightness for which you'll get a dipole. It's just an unfortunate thing we have to deal with. So
the white specks in that third frame, those are the dipoles, which are imaging artifacts. They're not real, right? They are.
So by dipole, I mean any point where you see a black and a white dot right next to each other. That means that. Mm-hmm. So in this case, I don't want to get into the details too much. It could be either caused by a bad astrometric solution, or in this case, differential chromatic refraction, in which stars of different colors actually move a little bit on the focal plane because of the atmosphere that they're passing through, shifts them up or down a little bit depending on how much air mass they're passing through.
Yeah, and chances are you would not see these as much in a Hubble difference image, simply because that you would see that maybe the changes in wavelengths if they had different wavelengths in them, but because there's atmosphere involved here, you can't remove that entirely, and you get these little dipoles. So you have one image minus another image equals what's left over, and that it shows up as bright or dark spots depending on which image was subtracted. And this is how you find things that change in the sky. There was something in one image that was not in another, and this is the easiest way to see it. But because of the sheer amount of data that are coming out of this telescope, and in fact out of a lot of different telescopes, you can't do this with a person looking at all of this, right? You have all of these terabytes of data coming down every single night. What do you process it on? Let me back up. Let's start with the data flow, and then we'll talk about how you find objects, because I think that's done automatically. You said you look at these things and you split it up into stars and galaxies and all this kind of stuff. But let's talk about the data flow first. It comes off the camera. What happens? Where does it go then?
It comes off the camera. We calibrate it.
There on the camera. By calibrating, you mean you do flat fields and dark subtractions, things like that?
That's right.
Okay.
Right after we take the exposure. We run detection, do measurement, do this difference imaging procedure, run detection and measurement on the difference images. This gets converted into a table of alerts. And these alerts are going to be distributed to the science community in real time, so that if there is supernova candidates or interesting features that need immediate spectroscopic follow-up, the community has this information available and can go follow up as soon as possible.
And okay, and then the alert system, can anybody join that, by the way? Or is it only open to other scientists?
Yeah, it's totally public, and everybody can subscribe to our alert stream. Now,
okay.
I forget the exact numbers, but it is it is a fire hose.
Be careful what you ask for, right?
Yeah.
Well, I'm sure.
And no difference images are clean.
Alerts, right?
So there's going to be a lot of false positives as well.
Right. Have you guys run? We did this in the Dark Energy Survey. Did you guys run simulations? Do dry runs of data flow and then alert systems and things like that? Have you guys done that?
We have not done that yet, but there are other time domain telescopes like the ZTF that are getting a head start on that and trying that out now.
Okay. All right. Well, so Frossie, what can you add to this? What after the alert system? Can you tell us what happens to the data once it's taken and the alerts have been sent out? The calibrations, is that a final calibration, by the way, the one that's done on the fly?
No, sorry.
Oh, go ahead.
It's not a final calibration, and like I was started saying earlier, there's two modes of processing. There's this instant prompt on the telescope, immediate processing, and then there's also going to be an annual data release production where we're going to recalibrate all the images, do the stacking, produce the templates for the difference imaging procedure, and do the types of processing that you need for static sky science, weak lensing, any kind of statistical studies of variability, any types of studies where you need the best calibrated data possible.
Okay. And so Frossie, can you add some more about what happens after all of that? So
yeah, let me tell you what happens. So just if you were just caring about the practical data flow, because I think you asked about that, the data actually gets siphoned off the summit through our very fast network and arrives at our LSST data facility, which is located at the National Center for Supercomputing Applications, NCSA, at Illinois, where the software produced by Yusra's team will run on it in order to process the data. So as Yusra said, there are two kinds of data processing. There's the let's find the things that have changed tonight, right now, right this instant, and there's a very tight time budget for doing that. We are aiming to actually get alerts within 60 seconds of the shutter closing, which, if you actually think about all that is involved to do that, is a very high bar. And then there is the kind of more thorough, deep processing that has to go in order to get the sensitivity of the kind of the required from the kind of cosmological science areas, and that's part of the annual data release production that Yusra referred to. So I can talk a little bit about what happens now. So big data in astronomy is actually quite a new thing. Of course, you guys talk to the SKA folks and other projects that are coming online with very big data volumes.
SK is a square kilometer array. Just want to say.
That's right. We're terrible with our three-letter in astronomy. And so this actually is a big change in the way that astronomers interact with data. Now, as you know, the kind of traditional workflow has always involved, like, you go to a telescope, you take your data, you put it on your old-fashioned exabyte tape, and you take it home, and you put it on your machine or your laptop, and you kind of play with it, and you kind of try to understand what you're seeing, and then there's a highly iterative process when an astronomer looks at data. They kind of look here, they'll kind of look there, they try this algorithm, they try this other algorithm, and then finally they're satisfied and kind of say, okay, now I'm going to apply this algorithm to all the data. So that's the kind of way that astronomical discovery is made. Now, in the big data era, the data cannot come to you. There's just too much of it. Even the catalogs, just the database that is involved is petabytes in size. There are 7 trillion rows in the database of object measurements. And so if the data cannot come to the astronomer has to come to the data. And this is a kind of emerging paradigm in astronomy, which is instead of you taking the data and then running your code to it, your code has to go to where the data is. And instead, we need a facility for people to interact with the data the way they used to interact with on their local machines, but at the data center, so that we don't have to pay the penalty of the network transfer and storage at the astronomer's end. And so what are we doing for that is we're developing a science platform, which is a web-based environment to allow us astronomers to interact with the data with the same kind of level of power and insight that they did when they were diddling around in their own machines, but this time with where the data is. And if you like, I can show some of it to you.
Okay, yeah, that'd be great. And I want to point out something that I think is understated in what Frossie just said. The ability of getting these images and then automatically sorting them into these trillions of rows of objects where they're going to know right away. They're going to run software on all of these images and say, this is a star, this is a galaxy, this is a couple of galaxies blended together, and then they have to deblend them and set them apart. All of this work is happening on the fly, and the days are gone of you going to a telescope saying, I would like a night on this telescope, and I want to take all of these images of the Andromeda Galaxy, and then you go home with your little CD-ROM or DVD or whatever it is of your data. Those days are gone, because the amount of data that you get now, there's just nothing realistically able to just deal with that other than these kinds of data management systems. And one of the things I love about doing these Hangouts is I have a team of people watching them who love to do the math. And so Peter Q on Discord has just said 1 exabyte is 1 quintillion bytes. So he did the math. He figured it out for us. So that's what an exabyte is. So thank you, Peter Q. I appreciate that. Okay, so you want to show us something. You want to...
Yeah. I just want to say quintillion sounds like one of those like gazillion type made words.
Well,
or a cotillion. That's something you used to call back in Victoria days.
It stops mattering at that point.
I think Peter Quinn wanted to point out the quintillion for a reason.
Oh, I didn't catch that. A little self-serving there. Okay.
There you go, Peter.
Okay.
Shout out to you.
All right. Yeah. All right. We're going to try an experiment. She's going to share her screen, and I don't know how this is going to project. So I'll play with it. Be patient. Go ahead and share your screen, Frossie, and we'll see how this goes.
I'm doing this now, and I'm going to try keep this down in to 5 minutes. Which can you see my screen? Can you see my?
I think so. I'm going to make it a little bit bigger, but yeah, go ahead and show us what. First of all, describe what we're looking at.
Actually, you know what? I'm not sharing my whole screen. If I just want to share my window, so that will actually make it bigger for you on your end. Let me just try that. Let's see. Here we go. This should be better. Come on. If we knew what we were doing, it wouldn't be cold research.
That's right. That's right. We live on the edge here. At
Take risks here.
Okay.
All right. So I'm seeing something called a Firefly visualization demo.
Right. And so I just want to say that so LSST, we're very proud that it's a big open source development shop. All the software that teams like mine and users are doing is being released. It's actually on GitHub. You can find it, you can see it, you can play with it, and we're very, very proud of that. And we have valuable collaborations with a lot of other open source projects. And one of them is this fabulous project called Jupyter Lab. And some of you may be familiar with Jupyter Notebooks, and Jupyter Lab is the next generation infrastructure that's still in beta, but it's extremely successful and promising, and we have adopted it in a very big way. So Jupyter Lab is an environment that allows you to write typically Python. It's not just Python, but for astronomers, it generally is Python notebooks from your browser. The notebooks execute at the server end, and so they're running at the data facility where the data actually is. And this allows you to, it's a mechanism for actually bringing your compute to the data if you want to interactively play with it, as opposed to the kind of batch factory processing that Yusra was talking about for the science pipelines. And what I wanted to say was that, like you say, this is a new era, where we are in the kind of big data mode, but we're trying to give people the flexibility that they had in the kind of traditional era and not kind of take that away from them. So one of the things I love about the Jupyter Lab environment is that it actually, this is all running in my browser. There's no tricks. It'll run Chrome, Safari, whatever you want. Is that it comes with a built-in terminal emulator. So although I am running my browser, I can actually just interact with the environment in which my notebooks are running, just from a regular Unix command line.
So hang on, you just opened up a terminal window in the browser to interact with your.
I know, right? Isn't it great?
I know. I'm doing a double take here because at first I'm thinking, this is not all happening in the browser. You're sending this through HTTP back to the server.
That is correct, and wow. I have to say the first time I saw this, it blew my mind. We have come a long way, and so I just want to say that we have I'm just going to go geek on you for 2 minutes. Please bear with me.
Yep.
We have our system that we have built on top of Jupyter Lab can be deployed at the LSST data facility and is, but in this particular case, I have a deployment on the Google Cloud platform. So if you have a credit card and you go to your GitHub page and you get the system, you too will be able to have this for it. But remember to run everything down before it costs you a lot of money. So this is it. And now I want to show you something else. And then I realize we're going to run out of time. So
I want to get to some questions. So that was the terminal emulator.
Yeah, and now I just want to show you our display here. Firefly is the imaging product by the data management team based in IPAC in Pasadena. And what you see is here a kind of imaging interface. And then I'm going to put this on the side, which I can actually do in this environment. And let's see.
Now, ultimately, this is how people will interact with the LSST data.
That's right. You're getting a very sneak preview of how it's all going to work. And if I'm just going to make this run the rest of the notebook really quickly.
So down below is the notebook, right?
Right. So you see the notebook above, you see the Python code, and now we have, this is again, all in browser.
Yep.
You can now see, and what I'm going to blow your mind some more. You can move these widgets around inside your browser in order to get it kind of how you like
Holy
it.
moly.
And the last one, so you can get to your questions. Let's see, I'm going to put that there. And there is full brushing and linking between these three displays. And so I'm going to prove this to you by just clicking on a point here, and you will see the row in the table that represents that point is highlighted, and the little point on the graph gets highlighted, and you can select points in the graph, and it will select them on your table in your image and so on. So this is like us using technology that we are leveraging that exists out there in order to give people remotely the kind of experience that they had working with the data locally on their own laptops.
So I guess, first of all, hats off. Wow. I mean, that is truly remarkable. I know Tony and I were probably dating ourselves here, but back in our day. Quick question for you though. So this is all going to be accessible. Where will this be found? Is this something that even the public could log into and play around with?
So our education and public outreach team is working on ways to give public access to the system. Strictly speaking, this system is for LSST data rights holders, which of course includes all U.S. astronomers, and I believe there are discussions as to how to bring that to the amateur astronomical community, but that goes into kind of policy level, so don't get me in trouble. And so we are very, very excited that this truly gives people, and you could imagine a classroom, you don't have to install any software, you don't have to do anything. This notebook runs the software developed by Yusra's Science Pipelines team, and you didn't have to install it, you didn't have to get it, you didn't have to build it, you don't have to understand how it works. You just open your notebook and there it is for you to use. So we're very excited about this.
So this is why it's being housed, all the data at the NCSA in the Supercomputing Application Center, because all of this data is using supercomputers and super storage units to house and to serve all of this stuff. And so that's why it's actually going there. So that's amazing. That was a really good interface. And so this is what you do with large data sets. You don't have it sitting on your desk anymore. Everything is, I guess you can call it a cloud, but you really need a good, effective way to ask science questions of this data without ever downloading it, all of it yourself, only what you need. And then that also allows you to, one of the things I like about it is when you're writing a paper, you're all using the same software. So when you make a discovery and you find something out using this data, you can publish what you did in this system in the paper, and other people can then go back and do it. I can't tell you how many times, folks, a guy will publish a paper with software that they wrote in Fortran in 1963, and nobody else can even compile it to reproduce their efforts. This is huge. This is a big deal.
So that's right. And can I say that although this kind of interactive Python environment, it's absolutely not a replacement for the kind of algorithmic software environment that Yusra's team is developing. I mean, you still need to actually have hardcore algorithmic processing pipelines to churn through the data. But what it can help you capture is, if anybody has been experienced of being a grad student in astronomy, and you kind of watching over your supervisor's shoulder and he does some magic, and then he goes, oh, all you have to do is this, and he types like some incomprehensible IDL or God knows what in his command line, and then he goes, see, now you should understand, and you're going, what just happened? And so what this does is it gives you the ability to capture in a very reproducible, like you say, way, and in a very nicely presented way, the kind of interactive investigations that previously were just essentially oral history passed down from astronomer to astronomer and from supervisor to student.
Right.
And now we can capture them and share them with everybody and show our techniques at a very detailed, practical level, as opposed to just the theory of it.
And I can also hear. Okay, go ahead, Chris. Go ahead, Christian.
I was just going to ask, and I'm being asked in our chats. So, where will the data hub be geographically located? Is all this going to be on the mountain in Chile, or is it going to be
in CSA, right?
So there are a number of data access centers. So the U.S. Data Access Center will be in CSA in Illinois. There will be a data access center in Chile for Chilean astronomers. There are also planned data centers in France for that will probably serve European Union users. There is one being developed, I believe, in Britain. And so one of the reasons that we are very keen on this kind of general purpose technology advancements like Jupyter Lab is that now, as a data access center, you don't just need our data, you can actually take our software as well and provide the same kinds of services to your users that they would get if they were US astronomers in the US. So this is going to be a big change for the facilities that people can use when they're exploiting LSST data.
It's huge.
Amazing.
It's definitely a paradigm shift. So Hans Milling commented, never thought I would see a Linux shell in Tony's videos. What's that supposed to mean, Hans? I love Linux. I run Linux all the time. Absolutely. You're going to see them, and you'll see more. Now that you said that, I'm going to show you more Linux shells. Kemp de Jong wants to know how much processing is done. How big is the data center? That's sort of a vague question, but you want to maybe give us a sense of just how much computing power is being thrown at this data?
Sure. I believe the peak compute power, I'm just looking at my cheat sheet because I can't remember my own phone number. The peak compute power at the data center is sized to be 1.8 petaflops. Sorry. It's a... I mean, we feel like we're living in the future in this project. It's pretty amazing. The peak number of nodes is 1,750.
Mm-hmm. Yeah. Are you guys using, by any chance, any GPUs for this processing, or is it all just regular CPUs? Graphic, like video cards.
We're planning on using just regular CPUs.
Okay, I'm just curious about that.
Yeah, in general, I personally have found that the going down to specialized architecture never really pays off.
True, that is true. I mean, if you use those NVIDIA cards, you end up with very specialized.
Theoretical kind of physical simulations are kind of a special case, but in this particular case, I think having software that can run on a generic architecture is an advantage to everybody.
Yeah,
absolutely.
So Neil Yu was commenting about, will NASA use this to hide asteroids or whatever, or UFOs? First of all, you should know that NASA has nothing to do with this. This is actually not a government project, is it? I mean, I think NSF might be involved, but this is a corporation. This is not a government-funded thing, is it?
Okay. This is getting complicated. So the LSST is actually funded by the National Science Foundation.
It is. Okay.
Your taxpayer dollars, we thank you, and the Department of Energy, which has supported the camera building at SLAC. However, it is operated on behalf. We're not directly owned by the government. The LSST is operated by the Association for University Research in Astronomy, which is a non-profit organization, and it's operated on behalf of the National Science Foundation. I can tell you, I have not seen any men in black coats around yet, and certainly, if there's any nefarious plan to hide the data, I am personally not aware of it.
Yes, there's a big
awful
concern.
lot
Well,
of data.
because NASA does hide things, and it hides. It hid Nibiru from us for, well, it's still hiding. Things. But yes, it's no. The NASA is not really involved, although the National Science Foundation is. And this data, folks, you can go get it. I mean, Frossie just showed you how to interact with it. You're gonna have to keep track of your costs because it's expensive, but you can get access to this eventually. You're working that out, right? Isn't that what I heard you say, guys? You guys are still, how can amateurs get it? That also still being worked out. But this is not just a trivial thing. You don't just put a bunch of images on an archive and say, yeah, go ahead and have at it.
Right. So data rights is a kind of a specialized area, but the one things I can tell you that I am fairly certain I am correct on is that the alerts, as Yusra said, are public. So the alerts of object changing in the sky will be available to anybody. The data itself is going to be constrained to countries that have data rights, of which the US is one, the UK is one, France is one, Chile is one. And so if you're watching this and you're not in one of those countries, lobby your representatives to get LSST data access for your scientists and your community. And we are planning citizen science projects through Zooniverse. We are planning public outreach to kind of school populations and also to provide certainly parts of this data for the general public to understand more of what it is that we do.
Okay, and we didn't actually talk about this, so we need to mention it before we go, and then we got to go because we're already past time. What is the projected first light? When are we going to be starting? When are we going to turn this thing on?
So in your Google Drive there, you have a timeline sketch. And of course, you know, it's projects are what they are. But right now, as you can see, the full science operations is scheduled to begin in late 2022. System first light is in kind of early to mid 2021.
Okay.
And that is what where we're currently working towards. So it's starting to not feel so far away right now.
You guys getting stressed out?
No, I'm getting excited. This is going to be awesome.
Well, that is great. Well, okay, so a couple years away, we're going to be looking at some first light images from the Large Synoptic Sky Survey or Large Synoptic Survey telescope. I always want to put sky in there for some reason. It should be the LSST. And so I want to thank you all. Thank you guys for taking time out to talk with us.
Thank you so much.
This. And we will keep you guys posted on future developments. We're going to try to get some more members of the LSST team as the project progresses, and hopefully we'll learn. We'll get some more news as to whether the schedule is still on track or not. So, so my guest today, let me just reintroduce them. It was Dr. Yusra AlSayyad. She's the postdoc and she's working on the science. She's a technical manager of the Princeton data management team. Also, Frossie Economou. She's the technical manager of the Tucson data management team, and that should tell you something. If there's data management teams all over the place, there's a lot of data to deal with. So, I want to thank you guys so much for taking time out to talk with us about your project, and we hope you'll come back and tell us more as time gets closer. Will you do that for us? I always love putting the guests on the spot. They're like, what am I supposed to say? No.
Absolutely no. Yeah, as you can tell from the fact that we ran over, we really like talking about this stuff.
Well, thank you so much, and
thank you so much.
Thank you so much for joining us. And I just want to say thank you, Tony, for streaming this on my channel, and thank you all watching on Launchpad Astronomy on YouTube. Thank you so much for joining us and experimenting with us a little bit. It seems like things worked out this time, so we'll be doing some more of these.
Yeah, we'll co-stream today. I think I've got PZ Myers tomorrow to talk about the origin of life, and Carol Christian and I will be around on Thursday with our Astro Coffee Hangout. So I want to thank you all so much for watching, and as always, keep looking up.